Hello and welcome to my talk about zero-shot cross-lingual transfer in legal domain using transformer models. My name is Zain Shaheen. I'm a PhD student at ITMO University and this is a joint research with my supervisors Gerard Wolkenant and Dmitry Mormtsev. A little bit about me. I am an ACM ICPC World Finalist and I have a bachelor degree in software engineering, a master in applied computer science, and I am currently a PhD student at ITMO University. And since 2020, I am a machine learning engineer in Huawei's Research and Development Center in St. Petersburg. In my agenda for this talk, multi-label text classification, definition, and the motivation for this work. What is cross-lingual transfer learning? What are the datasets that we used in our work? Our trained models, architectures, and so on. The training strategies that we used in training the models. Then I will show the results and evaluation studies results. And then I will conclude with a summary of this work. So first, what is large-scale multi-label text classification? It is the task of assigning a subset from a collection of thousands of labels to a given document. There are many challenges connected with this task. First, the distribution of labels is usually sparse and follows the power law distribution. Another challenge is the availability of large dataset to train a good model that generalizes well to unseen data. Collecting and annotating such datasets is an expensive and cumbersome process. Annotators need to read the entire document and check against all available labels to decide which labels to assign to the document. Furthermore, it is very likely that annotators are missing some potentially correct tags. Another application for this idea is that we can select some tags and filter a collection of documents and keep only the documents that correspond to these tags. And also we can find similar documents to an input document by first annotating this document and then use the previous filtering idea to keep the documents that correspond to the tags of the input document. So what is cross-lingual transfer learning? The idea behind cross-lingual transfer learning in text classification tasks is to use a representation of words or documents. These representations are extracted using a multilingual model, and they should be independent of the language and capture high-level semantic and syntactic relations. Through transfer learning, it is possible to train a classifier using a dataset in one or more languages and then transfer knowledge to different languages. This transfer learning approach is well suited for low resource languages and for tasks requiring a lot of data. The performance obtained with cross-lingual transfer learning aims to be as close as possible to training the entire system on language-specific resources. There are different schemes for cross-lingual and multilingual document classification, which can be distinguished by the source and target languages, as well as the approach of selecting the best model. In the zero-shot learning scheme, the source languages are different from the target languages, and the selection of the best model is performed using the development set from the source languages. In target languages or in target learning scheme, the source and target languages don't overlap, but the model selection is performed using the development set of the target languages. In a joint learning scheme, the source and target languages are the same, and the selection method is applied using the development set of all these languages. Let's move forward to talk about the datasets. Our datasets or the datasets that we used in our work are annotated using descriptors from Eurovoc thesaurus. The Eurovoc thesaurus is a multilingual thesaurus thematically covering many of the activities of the European Union. It contains 20 domains. Each domain contains a number of micro-thesauri. Descriptors in Eurovoc are classified under these micro-thesauri, and each descriptor belongs to one or more micro-thesauri. In total, there are 127 micro-thesaurus and 221 descriptors. We performed our experiments on two datasets. First one is multilingual GRC Aquis dataset, and the second one is multilingual Eurolex 57K. The first dataset, GRC Aquis, contains parallel documents in 20 languages. This dataset overlaps with Eurolex 57K and also contains additional documents. It is labeled using descriptors from Eurovoc, as I explained before in the previous slide. We selected documents in English, French, and German for our experiments in this work. And in table 1, there are statistics about this dataset. We don't use unlabeled documents for classifier fine-tuning, therefore we don't assign them to any training split, but we use them only for language model fine-tuning, as I will explain later. About Eurolex 57K multilingual, the original Eurolex 57K documents are legal documents from the European Union, labeled using a set of Eurovoc thesaurus descriptors. We collected parallel documents in German and French to the documents in Eurovoc or to the documents in Eurolex 57K. We extended our dataset by including Eurolex documents that are not available in Eurolex 57K. We use these additional documents only for language model fine-tuning stage, and they don't have a training split, and we don't use them in classifier fine-tuning. Statistics about this dataset is explained in table 2. So about the models, our work is based on BERT and DistilBERT, the multilingual version of both of them. BERT is a transformer-based architecture trained using masked language model and next sentence prediction objectives. BERT uses a special token CLS, which is added at the beginning of the text by the tokenizer, and this token reflects the hidden representation of the last layer and aggregates the sequence representation. We use the representation produced by BERT for this token and feed it to a classifier to classify our documents. The distilled BERT is a distilled version of BERT. It achieves over 95% of BERT's performance while having 40% fewer parameters. In our experiments, we used distilled BERT to select the best training strategy for computationally expensive experiments. And then we apply the strategy for multilingual BERT. About the multilingual training, to train our multilingual cross-lingual model, we fine-tune the transformer-based model, distilled BERT or BERT, using multilingual documents from the legal domain. The datasets I talked about them before. Then the classifier is built upon the document representation produced by IMBERT multilingual BERT model. We pass this representation of CLS token through a fully connected layer and then project the output to a vector of the size of the target class's count. To achieve the best results for our work, we use some training strategies. The first one is language model fine-tuning of the transformer model, where we fine-tune the transformer model before using it in classification. Fine-tuning is done on all training documents and additionally on unlabeled documents available in the URLex database. This step aims at improving the model's representation of legal documents. The second training strategy is gradual unfreezing. We freeze all the model's layer with the exception of the last few layers. We start by training only those layers. Later, the number of unfrozen layers is gradually increased during training. We provided ablation studies about the effect of using such training strategies on multilingual models trained in zero-shot learning and joint training schemes, and I will show the results in later slides. As a baseline for our work, Shaheen and all investigated the performance of various transformer-based models, including BERT, Roberta, and distilled BERT, in combination with training strategies like language model fine-tuning and gradual unfreezing. So we used these results of their work as a baseline to compare our results on the English part of the datasets. However, to best of our knowledge, there is no baseline exists for text classification using URLex and GRC Acquis for French and German, for which we provide a reference evaluation for both the joint training and zero-shot schemes. To evaluate our work or our models, we use F1 score as a decision support metric. This matrix focuses on measuring how well the system helps to recommend correct labels, and it aims at selecting relevant labels and avoiding irrelevant ones. These metrics have a measure drawback. They are targeted at predicting relevant labels regardless their position in the list of predicted labels. And as a result, this metric is not suitable for applications like recommendation system. So we use additional retrieval measures for evaluation, like relative precision at key and NDCG at key. These rank-aware metrics emphasize being good at finding and ranking labels. They reward putting relevant labels high up in the list of recommendations and penalizes late recommendation of relevant labels. Now I will show the results of multilingual transformer-based models trained in zero-shot scheme and joint training scheme, and also ablation studies. Let's start with zero-shot results. Here we evaluated multilingual transformer-based models trained in zero-shot scheme to classify French and German texts using only English texts as training data. In Table 3, it shows the results on GRC Aquis dataset, and Table 4, the results on multilingual Eurolex 57K. In our experiments, multilingual BERT consistently outperforms multilingual distal BERT in the zero-shot learning scheme by a large margin across both datasets, and we observe that better classification performance for the French dataset than for the respective German datasets, both for multilingual BERT and multilingual distal BERT. Here we continue to evaluate the multilingual transformer-based models for that we trained in joint training scheme. In Table 5, there are the results on GRC Aquis dataset. We observe that transformer-based models trained using GRC Aquis in joint training scheme fail to reach the performance of monolingual models on the English test set. In this manner, multilingual models achieve about 96 to 98% of the performance achieved by monolingual baseline models. Interestingly, both multilingual distal BERT and multilingual BERT perform similar performance according to all metrics, with slightly better performance for multilingual BERT on F1 score, and slightly better performance for multilingual distal BERT on the rest of the metrics. In Table 6, there are the results on Eurolex 57K, or the multilingual version of this dataset. In contrast to GRC Aquis, for the multilingual Eurolex 57K, multilingual version of BERT achieves similar or slightly better results on all metrics than Roberta, which is the best baseline model when comparing multilingual models to the monolingual baseline. Also, multilingual BERT achieves an improvement of about 1% over monolingual English BERT on all metrics. Also, monolingual distal BERT achieves slightly better results than multilingual distal BERT. Results are also identical. Comparing the results of zero-shot scheme to zero-shot scheme that we showed in the previous slide to the results of joint training scheme in this slide on French and German test sets, the experiments show that multilingual BERT trained in zero-shot scheme reached about 86% of the performance of the model trained in joint training scheme. In the same way, multilingual distillbird in zero-shot setting achieves about 79% of the performance of joint training scheme. Additionally, the multilingual models trained in joint training scheme on English, French, and German provide similar performance on their respective test sets. However, when using the zero-shot scheme, there is a discrepancy between French and German results, indicating that the multilingual models can more easily transfer from English to French representations. In this set of experiments, we studied the contributions of different training components and training strategies on the ZSL model by excluding some of those components individually or reducing the number of training epochs. In the following table, table number 7, gradually unfreezing the last 5 layers while keeping first and embedding layers, freezing achieves the best performance on French and German test sets. Unfreezing all layers obtains very close results to the best results on the French test set, while the difference on the German test set is a bit larger. Here we test the effect of the number of language model fine-tuning epochs. We noticed that on the French test set, one cycle of language model fine-tuning leads to about 20 of the relative gain compared to no language model fine-tuning at all. Increasing the number of epochs to 5 and 10 increases the relative gain to 29 and 32 correspondingly. However, the difference is much bigger on the German test set compared to no language model fine-tuning at all. The relative gain is 49% if we fine-tune the model for one epoch, 70% if we fine-tune the model for 5 epochs, and 76% if we fine-tune the model for 10 epochs. And the following table provides a comparison of the evaluation metrics with or without gradual unfreezing. For both French and German, we can see consistent improvement of the results when using gradual unfreezing. The relative improvement for French is in the range 38 to 45%, and for German is in the range 58 to 70%. In conclusion, gradual unfreezing is a crucial component for good classification performance of the model trained in the zero-shot learning scheme. To conclude this presentation, we evaluated cross-lingual transfer learning for a large-scale multi-label text classification task based on 2 datasets. The first one is GRC Aquis dataset and also an extended version of Eurolex 57K dataset. We started also a baseline for large-scale multi-label text classification based on these 2 multilingual datasets, which contain parallel documents in English, French, and German. We also compared between 2 cross-lingual transfer learning settings for this task, zero-shot setting and jointly training settings. The main contributions of this work are the experiments with multilingual bird and multilingual distillbird, with gradual unfreezing and language model fine-tuning. We also provided a new standardized multilingual dataset for further investigation and also evaluation studies to measure the impact of various training strategies on zero-shot and joint training transfer learning. There are multiple angles for future work, including potentially deriving higher performance by using hand-picked learning rates and other hyperparameters for each model individually. Moreover, experiments with language adversarial training and various data augmentation techniques are candidates to improve the classification performance. Thank you.